Hi, I'm Tim Asowski, a PhD student at the University of Wisconsin-Madison. Today I'll be presenting OctoMed, data recipes for state-of-the-art multimodal medical reasoning, which has been accepted to CVPR 2026. This project is about figuring out, in a principled way, how to train a strong multimodal medical reasoning model, specifically what data and what training procedure would work best. When I say reasoning chatbot, I mean a model in the style of DeepSeek R1 or OpenAI's O1 reasoning model. Basically, given a question and image, the model first produces an internal chain of thought inside think tags, working through the problem step by step and ruling things out, and then it commits to a final box answer as shown in this example. So the model in this example is shown a brain scan and walks through which imaging modality could produce it and correctly identifies it as an MRI. The think trace is what makes this a reasoning model rather than a standard chatbot. At a high level, the problem looks like this. We have a large collection of multiple choice medical questions. Some are text only, or some have an accompanying medical image like an X-ray, CT, or MRI, and we want to train a vision language chatbot that can reason through these questions and produce the correct answer. So the research question here is, how exactly can we get from this raw data on the left to a strong reasoning model on the right? More specifically, the concrete research question is, what is the best training and data curation recipe for building a 7 billion parameter multimodal reasoning model in the medical domain? And we chose 7 billion parameters as a sweet spot, which is small enough to be run on a single GPU in a hospital-specific environment, but also large enough to be competitive with much bigger frontier models on medical benchmarks. We considered two post-training methods. The first is supervised fine-tuning, or SFT. Here we hand the model fully worked out reasoning traces, for example, this question about enzyme replacement therapy, and the model learns structured reasoning by imitation. So it essentially copies the style and structure of the reasoning traces it's shown. The second method we consider is reinforcement learning, or RLVR. Here we don't give the model any reasoning trace at all. Instead, we only give it the question and let it explore by itself and generate many candidate reasoning trajectories on its own. And we only reward the reasoning trajectories that end up giving the producing the correct final answer in a box. So the model learns to reason by trial and error, discovering reasoning strategies that actually lead to correct answers. So both of these post-training methods have pros and cons. So for the pros for SFT, it's really fast to set up and it runs quickly and it scales easily to over 1 million examples. And it's great for injecting domain knowledge. But the downside of it is it requires reasoning traces, which we have to generate somehow. And it also suffers from catastrophic forgetting when you fine-tune sequentially on new tasks. And it can also overfit if your data curation is sloppy, or your training is sloppy. RLVR, on the other hand, generalizes much better and is much more sample efficient, but the downside is it's really expensive. You need GPUs for both inference and updates. And it's really slow because you need many rollouts per sample, and something really important is also you need a strong base model to start with to do RLVR. Otherwise, the reward signal is too sparse. The model might never produce like strong reasoning traces to learn from. So given our compute budget and the scale of medical data we had, we decided to focus on SFT for this work. RL is a great direction for follow-up, which I'll touch on at the end of the talk. So choosing SFT raises some immediate questions. So the first is like, where do the reasoning traces actually come from? We don't have a database of doctors writing out medical reasoning, and it's very expensive to get them to do that, so we need to generate them somehow. One option is to use guided distillation. Specifically, we feed a strong teacher model both the question and the correct answer, and we ask it to produce a justification for how do you get from that question to the answer. So the good thing about this approach is you would use every single question and answer pair in your data set. The downside is that even with the correct answer, the teacher can potentially hallucinate some clinically incorrect reasoning to justify getting to the correct answer. The other option is rejection sampling. So the teacher only sees the question, not the answer. In this case, it generates a reasoning trace and the final answer, and we only keep the trace if the final answer is correct. So a nice thing about this approach is the reasoning is much more likely to be clinically valid, although it's not guaranteed, because the model arrived at the right answer on its own. The downside is that for any question the teacher consistently gets wrong, we throw away all those examples. So for our first design choice in the recipe, we decided to use rejection sampling when the answer is verifiable, and fall back to guided distillation if the answer is not verifiable. What should we use for the teacher model? We tested several state-of-the-art models such as DeepSeek R1 and GPT-4o across text-only and multimodal medical tasks. And from our experiments, we found that DeepSeek R1 was an excellent teacher for the text-only medical reasoning, as you can see here. But on multimodal questions, it falls behind GPT-4o, mainly because, DeepSeek doesn't have multimodal encoder. It's a text-only model. So instead of picking one teacher, we use both GPT-4o for questions with images and DeepSeek R1 for text-only questions. Pipeline, we decide to use DeepSeek R1 for text-only tasks and GPT-4o for multimodal tasks. Next major design choice, we consider how many rejection samples should we generate per question. If we generate just one sample per question and we get exactly one reasoning trace and it happens to be wrong, like in this case, we will lose that question entirely. With two samples, we get two independent reasoning paths, so even if both arrive at the same correct answer, the intermediate reasoning can be quite different, which gives the student more variety to learn from, and we also get a higher chance of sampling a correct reasoning trace. So if 4 samples, we can get even more diversity, and similarly, like as we keep scaling this up, we have more likelihood of getting correct reasoning traces and increase the diversity. Here's what we found from the ablation study we did on this phenomenon. In the early regime, adding rejection samples behaves a lot like training for additional epochs. The model is essentially seeing the same questions more times, and it's hard to tell where the gains come from more diverse reasoning or just more gradient updates. However, as you scale up further, rejection samples improve generalization in a way that extra epochs do not. The peak performance with 16 rejection samples is meaningfully higher than what you'd get by just training longer on a smaller set. So the diversity of reasoning generally matters beyond just exposure. We settled on 16 rejection samples per question over 3 training epochs as our diversification strategy. The next part of our pipeline was the filtering of reasoning traces. Basically, not every question is equally valuable for training. If a question is too easy, the teacher model already knows the answer, it's kind of a waste of compute to train on that question. At the same time, if the question is hopelessly hard and the teacher model never gets it right, the reasoning trace would probably be wrong anyway, or the question is of poor quality, so we also want to throw away those. So we ideally wanted to filter for questions in the sweet spot, where the teacher sometimes gets it right and sometimes gets it wrong. So we called this technique teacher proportion filtering, basically using the teacher's accuracy as a difficulty signal. An alternative where we use the student model instead of the teacher model as the filtering agent. So basically, the student generates samples and we use its accuracy on a question to decide whether to keep that question in the training set. The last filtering technique we considered was LLM judge filtering, where we ask LLM, we give it the question and answer, and we ask it to directly rate the difficulty of the question-answer pair on a difficulty from 1 to 10 scale. Applied all of these filtering strategies and compared to a baseline no filtering training run, and we found that all three methods significantly improve the sample efficiency, so we can hit a similar peak performance with substantially less training data, which matters a lot in compute constrained settings. However, the peak itself doesn't really go much higher than training on unfiltered data, but you can get there potentially faster. Together, this is the full data recipe. First, using rejection sampling with an appropriate teacher, followed by 16 samples per question across 3 epochs, and finally, optional filtering. There are some more ablations we did. I'd recommend checking out the paper and appendices for more details about that. All the steps just laid out explicitly. Recipe and scaled it up. And here's a breakdown of the training data we curated. It's a mixture of text-only and multimodal medical question-answer sources spanning multiple specialties and imaging modalities. The diversity here is important for ensuring that the final model generalizes across medical domains and modalities. We fine-tuned our QN 2.5 VL7B instruct model on our dataset, and we found that the result, OctoMed, achieved state-of-the-art performance among 7B scale medical reasoning models across these diverse benchmarks. We're also competitive with, and in many cases beat, much larger frontier models, which validates that careful data curation can be a substitute for just training larger models in this domain. Conducting our training and experiments, we observed a few directions for future work. So first, we think adding an RL stage on top of our SFT model should be much more practical since we now have a strong SFT baseline. Another thing we want to consider is visually grounded reasoning. So right now our models only output text reasoning and basically reference the image or talk about it at a high level, but we'd like to see if it can also include bounding boxes or segmentation masks within its reasoning trace. And lastly, we think that currently medical multimodal benchmarks lean very heavily on text reasoning. In fact, for some benchmarks, completely omitting the image results, you can still get a pretty decent score on those benchmarks. So building some benchmarks where it's truly necessary to reference specific parts of an image will be important for evaluating the next generation of models. And that's it for our work on OctoMed, and thank you so much for listening.